Give me 1 second. Good morning, everyone. I believe you can all hear me clearly, right? Okay. I want to welcome you to another statistical topic. Today, uh, I'm actually going to be walking you through what I call decomposing the variation of y. Okay, so I think before this topic is going to make sense, I need to first, have a recap on what we've done before. We started by trying to characterize relationship between two variables, one dependent and the other one independent. The dependent is actually denoted by letter y, while the independent is x. We are seeking straight line relationship. Of course, I've walked you through how you can specify linear regression models to do that. In this class, I've walked you through how to estimate parameters in linear regression model. And I remember the last time we met, I also walked you through some assumptions underlying the use of linear regression model. But what we want to do today is to tell you, as part of the goal in statistics, because one of the goals in statistics is model explanation. I'm going to say that again. One of the goal in statistical world is what I call, we pursue what we call a causal goal, okay, an explanatory goal, which I'm going to write that for you to be able to see, okay. We pursue a causal goal that we also call explanatory goal, okay. What do we mean by that? You know, that is synonymous with basic science. Basic science. In basic science, we have basic science, we have applied science, right? Okay, in basic science, we try to understand the world. We try to explain the world. One of the goals in statistics is also to pursue that goal, explanatory goal. Okay, and if we understand that, then we will be able to go for applied science, which is basically using the knowledge, okay, to make a prediction, which I'm going to call predictive goal. Today, I'm actually going to tell you how we can decompose the dependent variable into uh, two different sources of variation, because we believe there is 100% variation in the dependence. Okay, and we actually want to know how much of the variation is explained by the independent variable and the one that cannot be explained. Okay, so to pay attention to what we're actually going to be doing. Okay, today I want us to be practical. Take a look at this animal. It's called kangaroo, right? There's a male kangaroo. Okay, we actually studied the NASA weight of male kangaroos. Okay, the NASA weight, that very NASA weight, we're going to denote that as Y. That's a dependent variable. Okay, so if I actually want to figure out the NASA weight of male kangaroo, what I'm basically going to do is to collect, to take a sample of male kangaroos. Then I'm actually going to have a measure. Like here, we're choosing 45 kangaroos, 45. And on each kangaroo, we measure the NASA weight. Of course, because we live in a stochastic world, we expect the figures not to be the same, right? They're going to vary, right? Okay. And in order for us to actually take a position, what we're going to do, we're actually going to find the average. You see that? Summation y divided by 45, it means we are adding the NASA weight of 45 kangaroos. What do we get? That gives us 244.16. So that 244.16 is actually the mean. Now, this is the question that we now want to ask ourselves. How much total variation exists in Y? I told you the other time, in terms of percentage, it is 100% variation that exists in Y. What is Y here? The Y is the NASA weight of the kangaroo. Okay. Now, the how much now, we're not interested in percentage now. We're interested in absolute numbers, like what is the total variation around kangaroo? Of course, you know there's going to be variation around kangaroos. That was why we're finding the average. We don't find average if there's no variation. I think you know that. We find the idea of the average comes in because of the fact that there's variations. There's going to be variations in measurement. You got 45 kangaroos. Of course, you're going to have 45 different values. And that was why we said, how much total variation exists in Y? If I really want to know that, okay, I can put that to say how much Y deviate from the center. What I want to do now, okay, the center is the mean, and you basically want to know how far apart is the mean from the respective observation. Okay, like I said, the 45 kangaroos that you measure actually go from maybe 200 to, you can see the plots, right, for the 45 kangaroos, and of course that's what the center, the 244.16. Now the question now is, okay, we basically want to measure how far apart that center, the 244.16 that we got, from the respective observation. Okay, if you want to do that, you're actually going to be subtracting the center from each NASA weight of the kangaroo. Don't forget we got 45 of them. Then when you subtract them, you're going to square. Does that make sense? And by the time you're going to do that from Y1 up to Y45, don't forget, you got 45 kangaroo. Okay? So when you do that, the total of that will give you 40,196. You know what I've computed now? The total variation around the NASA weight of kangaroo is 40,196. And this is equivalent of 100% that I talked about the other time. Okay, this is a formula that we use. Summation y minus y bar all squared. Don't forget the y bar is the center, right? That is the mean, right? Okay, and that give us 40196. The 40196 is actually the total variation around the dependent variable NASA weight. Okay, now you know what we want to do now. We have a good news. When we were looking at the NASA weight, the good news that we have now is we have information about NASA length. When I have information about NASA length, okay, what is making it a good news is, can we have a way to represent the NASA weight and the NASA length by a straight line relationship, so that with the information, if I have NASA length, if I know something about NASA length of a kangaroo, can I make a prediction of the NASA weight? Does that make sense? That's what I want to do now. Okay, so that also I said good news. My colleague collected the NASA length of these 45 kangaroos. But let me tell you, the same kangaroos. This NASA length is coming from the same 45 set of kangaroos that you actually observe the NASA weight. Does that make sense? Okay. Now, we're going to call the NASA length X. We call the NASA width Y. Does that make sense? Okay. I said, let us now, the moment you have that, of course, you know where to start. In statistics, I told you, the part of the preliminary investigation, when you are trying to seek a relationship between two variables, is to generate a scatter plot. Does that make sense? Okay, the scatter plot is a diagrammatical plotting of the dependent variable in the vertical axis against the independent variable in the horizontal axis. As you can see now, we've plotted the weight, the NASA weight against the NASA length. Any question? Okay, now, the moment we get that, we shouldn't forget that the center, okay, if you see the the red solid line, it's actually the average, the center of the NASA weight. Does that make sense? Don't forget that. Okay, now, what we now want to do now, the regression model, because we have fitted relationship between the NASA weight and the NASA length, now the question now for us to be able to justify, okay, fitting linear regression to them, then we want to be able to know out of the total variation in the NASA weight, how much of that can the NASA length explain? Does that make sense to you now? That's what we want to do now. That's what we say. The regression model explains some variability. Look at that. Look at the word some. It cannot explain all the variability. I told you from day one. Our model is not perfect, even though we want to capture reality. Our model cannot give us exact reality. The model cannot explain every variation in the response. Okay, so how do we do that? Because we want to say, when you know something about X, can we say something about Y? I need you to pay attention to this. No, you know X. I know NASA length. Can I say something about NASA weight? But let me tell you this. We cannot say everything about that, but we can say something. Okay? So that's why, we're trying to say it is not all variability in the dependent variable or the model we explain. Now, what we want to do now, how do we compute variation attributed to the model? When I say variation attributed to the model, I'm actually talking about, the variation attributed to X. What is X in this case? NASA length. How do we compute that? This is how we're going to compute that. Do you see Y cap 1, Y cap 2, up to Y cap 45? The only way we can get all those predicted value is if you've already obtained the beta naught and the beta 1 in this class now. Of course, you know how to obtain the beta naught and the beta 1. Okay, I'm actually going to write, you got Y cap, equal beta naught cap plus beta 1 cap X. Okay, this is NASA weight. Okay, and this guy is a NASA length. Okay, now if you get this guy and this guy from your data, you're actually going to get the predicted values. How many predicted values are you going to get? That will be 45 because you got 45 kangaroos. Okay, so what are you doing now? You are now subtracting the average. The average of what? You are subtracting the average of Y, that is the average of the NASA weight, from the predicted values. Then you square that. Then you add them up. When you add them up, what do you get? Oh my God. When you add them up, that gives you 31,227.9. And what was the total variation around the dependent variable? Was 40,000 something, right? Okay. Even though the regression was not able to explain the exact value, but this is very huge. Does that make sense? We actually want the variation explained by the model to be very huge. That is how we can trust the model. If the variation explained by the model is very huge, the unexplained variation will be very small. The unexplained variation is actually the error. We acknowledge the fact that model is not the same as reality, but you know what we want to do? You can only trust your model if we're able to minimize the error. The error here is going to be the unexplained. Now, let's see the unexplained. If I want to find the unexplained now, you know what I'm just going to do? It's going to be total variation minus this. Okay? Even though we also have a special formula for the unexplained. Okay, before I go into the unexplained, so this is the formula. This is the formula that we use, like the summation y cap minus y bar all squared. Okay, that was how we arrive at what you're seeing now. Okay, now the next thing now is basically there is still some variation in y that cannot be explained. What are we trying to say? Okay, we actually want to compute variation that cannot be explained by the length. Don't forget, we basically want to explain the weight of kangaroo using the information about length. But it is not everything that length can explain. That's what we mean. And we now want to compute that. That is what we're going to do. It's just going to be the actual observation of the dependent variable minus the predicted. Is that not the error? What is the residual? The residual is the difference between the actual observation and the predicted observation. That's exactly what you're saying now. Okay, so you're going to square that, and that is the reason why it's going to be called sum of square residual, or we call it sum of square error, because we square the difference and we sum them up. That's why it is called sum. So what do we have? That is 8,968.1. As you can see now, the unexplained variation is very, very small. You see that? Okay. Now, in this course, when you see ROSS, we call that residual sum of square. Residual sum of square. Okay, R is residual, SS is sum of square. Does that make sense? Which in some textbook, you can actually going to see that as sum of square error. Okay, we call that on the total unexplained variation. Unexplained. The one your model cannot explain. In this case, the one the NASA length cannot explain in the weight of kangaroo. So what are we talking about? What we're talking about now, oh my God, mathematically speaking, we've been able to decompose the variation around the dependent variable to the variation explained and the unexplained. Take a look at that. And that's why we're doing this topic, decomposition of the variation in the dependent variable. So what we're trying to tell you now is that the variation around the dependent variable, and in this case, the dependent variable is a NASA weight, and that has be decomposed by variation explained by the length of the kangaroo and something else. Something else is unexplained. Does that make sense? And that is the decomposition that I just talked about. Now, I'm actually going to use this as an example. I wanted to buy a soda, but I forgot I would have brought soda to this car. But I'm going to use this to explain. Can you see that guy? That's an orange, right? Orange, right? That's an orange, right? What do you want in orange? What is inside the orange? What is inside the orange is there. That is explained. The orange itself is a total variation. Okay? In the end, what is going to happen? Some other thing is going to go into a trash. What goes into a trash is the unexplained. And we're going to make sure We don't put a lot into a trash. What we want to put in the trash should be something minimal. And that's why in statistical analysis, we actually want to minimize the error. We acknowledge the fact that our models are not perfect. We acknowledge the fact that there's an error, but we want to minimize that. So that whatever that go into a trash is very, very small. Does that make sense to everyone? So the SST means sum of square total, the sum of square total, which we call the total variation around the dependent variable. While SSREG means sum of square regression. The sum of square regression is called explained variation. Okay, the variation explained by your model. While the ROSS is residual sum of square, which I call unexplained variation. Take a look at that. Total variation in Y. Variation in Y explained by the model. When I say by the model, I'm actually referring to the independent variable in the model. In this case, NASA length. And variation of Y unexplained by the model. No matter how you try, our model can never be perfect. And of course, unexplained variation can never be zero, no matter how we try. Does that make sense? There's always going to be that. There's going to also always going to be unexplained variation. Oh, those of you online, can you see confirm if you can see hear me clearly? Those of you online, can you confirm by talking if you can hear me clearly? I need someone online to confirm if you can see hear me clearly. I can see your chat now, and I only need you to talk. Can you hear me clearly? You see hear me? Is somebody see hear me online? Let me check. Is there anybody online? The somebody that is talking is muted. I need the person to talk if you still hearing me clearly. The person is muted. I think I'm going to make an announcement because I'm seeing, my experience shows that some students that time they will attend lecture online, but they're going to be far away from their laptop. So I can see only one person online, and I'm not sure if the person is in this lecture. Okay, I know what to do. Maybe I'm not going to allow online access, and the only condition I'm going to allow online access is when you actually go into it. Okay, that's what I'm going to do. I see somebody online now, but the person is not talking. It's kind of muted. Another person just joined. Can you confirm if you're hearing me? The person that's just joined. The person that is talking is muted. Can somebody chat with me? I want to see whether you are online. Are you online? Because somebody confirmed they can hear me the other time, but I'm not sure if anybody is on. Yeah, I need you to talk. Somebody said yes. I need you to talk if you can hear me.
I can hear you.
Oh, thank you so much. Thank you so much for confirming that. I'm gonna send a message today. Before I'm gonna allow anybody to attend lecture online. You just have to participate in whatever we're gonna be doing. Just like the same way people in class participate, you for the service. Okay, so I'm gonna continue from where I stopped. Okay, so some of you might have seen that formula that I'm displaying before. That is the formula to get the total variation around the dependent variable, the formula for the sum of square regression, and the formula for the residual sum square. Okay, I want you to take note of all of that. Then what you are trying to say is the degree of freedom. And I know some of you, before you see a degree of freedom that is n minus 1, you see another one that is n minus 2. The one for n minus 1 is the degree of freedom for the dependent variable. The one for n minus 2 is the degree of freedom for error. Please take notes. Okay? The same way the total variation around the dependent variable is partitioned into two, the same way the degree of freedom is also partitioned. Now, we want to go into coefficient of determination now. Do you know the meaning of coefficient of determination? You know, right now, I just walk you through how the variation around the dependent variable can be decomposed into two, into explained variation and the unexplained variation. The coefficient of determination will tell us how much out of the 100% variation in the dependent variable, how much of that can be explained by the model. Of course, that is going to be the ratio of what? The ratio of the explained variation to the total variation. And that's why you are seeing the SS reg divided by SST. Does that make sense? Okay, so if you multiply that by 100, you're actually going to get that in percentage. We also call that the goodness of faith of a model. That very particular value should be, we want to maximize it. We want to maximize R squared. The R squared is going to be in the range of 0 to 1. But if you really want to make sense, you're going to multiply. Now, let me show you where to get the R squared. You know, when you run your linear regression in R, there's going to be a lot of output that will come out. Where can you have the R squared? Check multiple, where you see the multiple R squared. Can you see multiple R squared? What is the value here? It's 0.7769. So the R squared will always going to be part of your regression output in R. Does that make sense? And if you want to make a sense of this guy now, you're going to multiply that by 100. If you multiply 0.7769 by 100, that will give you 77.69%. You know what that means? It means out of 100% variation in the dependent variable. What is the dependent variable here? The dependent variable here is a NASA weight of kangaroo. Okay? The NASA length of kangaroo was able to explain 77.69% out of 100%. A very reasonable R square should be the one that is at, that's at least 80. You know, when the student got 80%, it's like the student understand the course in a way. So we use this in model evaluation, this part of model evaluation criteria. Okay. Now, in a graphical way, okay, this is the decomposition I just talked about. We plot y against x. You have a scalar plot. You draw the line of best fit. Okay, and you have a mean. You have a center. The dotted line is the center. You actually want to decompose. Okay, you're going to see the decomposition now. I'm actually going to go mathematical. If you take a look at what I have, the yi minus y, the y minus y bar, the y cap minus y bar, the y minus that. Of course, we actually use each of that to be able to obtain the total variation in the dependent variable, the variation explained by the model as well as the unexplained. And this is what I'm trying to showcase here. You can see y minus y bar. You can see the color that I used to represent that in the graph. And y cap minus y bar, you can see the color, and you can see the other one too. So this is actually explaining the decomposition. That is explaining the composition. that I just talked about. Now, you know what I want to do now? For individual observation, because we believe that every data set, every data point is contaminated. I'm going to say that again. Every data point is contaminated. The same way you have an orange. Orange is contaminated. Contaminated with what? With that stuff that go into a trash. So which means what we always do in statistical analysis, when you get data, information is inside data. The same way that liquid content is inside the orange. So what do you now need to do? For you to be able to get the maximum information, let me ask you this question. If you have an orange, is it possible you are able to extract all the liquid in an orange? Is it possible? There's going to be lots of information. There will be some liquid content that will escape. That will be part of what you're going to trash. Does that make sense to you now? No matter how we do, you cannot extract all the liquid content the same way you cannot extract 100% information in the data. But you know what we want to do? We want to extract the maximum, like the most maximum, even though we know there's going to be loss of some, but we want to be able to minimize the one that will get lost. Now, what we want to do now, mathematically now, we basically want you to see the partition mathematically for each observation. The one you did the other time was for the total. Does that make sense? The total, like right now, as I said, for each individual observation, we have that. And when you now introduce a summation and the square, that becomes the total. Does that make sense now? There's going to be error associated, the variation around a particular value of a dependent variable. There will be total variation around all of that. So that's what you're trying to see. Okay, so this actually explaining the decomposition. If I write that guy and I squared, then I'm going to use a law in mathematics, a plus b all squared. A plus b all squared is going to be a squared plus b squared plus 2ab, right? Which is going to be this. Something like this. Do you see that? What am I using? What do you think we're using now? We're actually using the idea of mathematics. Okay? Statistics requires mathematical knowledge. A plus b all squared. What is it? A squared, b squared, 2ab, right? That's the idea we're using here. You square each of that, okay? And you do 2 times that guy. Okay? Take a look at that. Now, the next thing now, you're going to introduce a summation to both sides. What we're trying to tell the world is for us to prove for all observations, we're actually going to begin from each individual observation. That's exactly what we're telling the world. Okay, so when I introduce summation now, okay, the one with the 2, we can't, we become 0. Okay, the one in that rectangular box is basically going to become 0. Okay, we have put that mathematically. Then we're only going to have this guy, because that guy equal to 0. Okay, and if you want to find out how does it become 0, we can show the world. Okay, this is the way it becomes 0. This is the proof. If you're interested to know, at the end of the day, it becomes 0. You can read that. That is how it becomes 0. Whatever we do in statistics, we have a way to prove to the world. We apply the mathematical knowledge. Okay, this is the reason why that guy becomes 0. Okay, when it becomes 0, I'm actually only going to have just the first 3, okay, which is the one that I showed you before, that the total variation around the dependent variable can actually be decomposed into variation explained and the variation unexplained And that very the one in the rectangular box, this is how to show that is going to be 0. Now, the next thing I want to talk about now, who was responsible in splitting the total variation into explain and unexplained. I'm actually going to show you the scientist that did that, and he actually called that analysis of variance. The analysis of variance is the splitting or the breaking down or the partitioning of the total sources of variations into various components. When you split the variation around the dependent variable into various components, what are these components? The component like explained variation and the unexplained variation. So that's what I want to walk you through now. We call it analysis of variance. Okay. So the analysis of variance, we use a variance-like quantity, of course, such as what I just walked you through, the sum of squared total, the residual sum of squared, and the sum of square regression. Okay, so you all know that this is the formula to find the variance of y, right? If I want to find the variance, that's the formula. And this is just to tell you the difference between the variance and the total variation. The variance is the total variation divided by the degree of freedom. What did I call the degree of freedom for the dependent variable the other time? N minus 1. So if I want to find the variance of the dependent variable y, the variance of the dependent variable y is going to be the ratio of the total variation by its degree of freedom. The degree of freedom is N minus 1. So I'm just trying to, I wanted to say the difference between the two. Okay. F-test is an example of ANOVA, a statistical analysis. I know you've heard about ANOVA test. It's also called F-test, where we compare the means of more than two populations. But that is not only thing that we use F-test to do. We also use F-test to, if we partition the variation around the dependent variable into various components, F-test can also be used in that regard, for us to be able to know how adequate is our model. If I want to know how adequate is our model, then I need to conduct an F-test. When I say how adequate is our model, is the straight line significant, right? And with the F-test, I will also be able to use an R-squared, which is the coefficient of determination, where we'll be able to know how much percentage of variation in the dependent variable the model was able to explain. This was put forward by this man, George Snedeker. The George Snedeker, in conjunction with Ronald Fisher. Yeah. Okay. So they actually put forward analysis of variance tests. And of course, with their efforts, the variation in a dependent variable can now be partitioned into various components. Now, like I said, Snedeker name it after Ronald Fisher, for his pioneering work in the analysis of variance. Now, the ANOVA test will make use of F distribution. That's what I'm trying to show now. The F distribution, we have two different degree of freedom. Okay. With different degree of freedom, you're actually going to have different shapes. Okay. That's exactly what you're saying. But you know what I want us to do? I want to take you to how can we do this in R, which my TA. Take a look at these results. What you are seeing now is when you run a linear regression code in R between the NASA width and the NASA length of kangaroo. By the time you press summary into that, you're going to get all of that, right? Now, what is the meaning of, you can see estimate, standard error, t value, and p, right? That p is what we call p value. Now, when you take a look at the p-value, you can see 1.34, whatever. That is a p-value associated with slope. If I want to investigate how significant is the slope, I got a model. How significant is the slope in my model? I'm actually going to use a t-test. That is why you see a t-value. The t-value here is 12.24, and the corresponding p-value is that. Okay, which I'm still going to walk you through later. But I just wanted to say that what came out of the linear regression output in R, you're actually going to get a lot. You're also going to see another p-value. Do you see another p-value? You see F statistic, you see another p-value. That there are two different p-value, one for the individual, and the other p-value is for the overall parameter in the model, which I'm still going to explain. Okay? Which I'm still going to explain. But you know what? If I want to conduct an F test, I'm actually testing whether I should use an intercept model or I should use a full model. For the case of kangaroo, you know what the intercept model is talking about? The intercept model is trying to say, if I want to determine the width of a kangaroo, we don't need information about the length. Does that make sense? If you don't need information about the length, what does that mean? Under the null hypothesis, the beta 1 equal to 0. When the slope equal to 0, it's actually telling you there's no connection between the two variables. What about the alternative? If the alternative is going to say, oh, beta 1 is not equal to 0, if beta 1 not equal to 0, that implies there's a relationship. There's a connection between the two. Okay? So take a look at that. Now, the test statistic that we use, this is the formula. But let me tell you this, that value has already been given in a table. Okay? So I'm going to quickly take you there. This is the summary table. If for me to be able to conduct that test, I will look at the p-value here, the one I underline. Okay, you see F statistic, that is for the F test, and this is the p-value. Okay, now how do I know whether I should reject or not? What am I testing? Don't forget, I'm testing whether beta 1 equal to 0 or is not equal to 0. If beta 1 equal to 0, it means there's no connection between the width and the length of kangaroo. But if beta 1 not equal to 0, it means there's a connection between them. There's a relationship between them. Now, we got a p-value now because R will automatically return p-value. Okay, and let me tell you this. If you want to take a decision regarding whether to reject or not, you're actually going to compare the p-value with the level of significance. The standard level of significance is 0.05. What is the meaning of level of significance? That is a level of statistical error. Okay, 0.05 means 5%. It means out of 100, we are misleading the world 5 times. That's okay. There's no way we cannot mislead the world in our research. We're going to mislead the world. But provided, this the type 1 error rate is not going to exceed 0.05. So what we're going to do now, you're going to compare the p-value there, which is 0.05. If p-value is less than 0.05, you reject HO. I'm going to say that again. When p-value of a test is less than the given level of significance, the null hypothesis will be rejected. When the null hypothesis is rejected, you know what that means? It means there's a statistical, it means the relationship between Y and X is statistical significance. Does that make sense now? Okay, and that is exactly what you are saying. Now, if I now want to look at the decomposition that I talked about the other time, then I need to do ANOVA. Okay, I need to do ANOVA. Okay, MOD is equal to LM, right? your Y on X, like you know the code. Now, when you do ANOVA into MOD, it's going to bring you, it's going to give this. Now, let us make sense of what you have here. Okay. This is going to be the same as that. It's either you conduct this or you conduct that. You actually going to take the same decision. But in the ANOVA table, what is the sum of square? You see 31227.9. That is the explained variation that we computed manually the other time. What about 8968.1? That is the unexplained variation that we computed the other time manually. Then can somebody tell me, how will I get the total variation? Because the total variation will not come as part of the ANOVA output. Okay, then you just add it too. Send me a message for extra credit. Make sure you, I don't joke with my extra credits. I don't know that you know that. You can use your extra credits for maybe for assignment, midterm, and the final. So please keep track of that. So you need to send me a message for that. Okay, so you can see now. So this is how you basically going to do that in our. Okay, finally, a second. Just okay. I think it's gonna go. Yeah. For finally, I think that is all what I got for you today. The other one is just gonna be yeah. So the same analysis. So this is the analysis of variance table. If you're giving this analysis of another thing I needed to know, the column, the gap relationship. If you look at how do I get the mean square, sum of square? It is the sum of square divided by degree of freedom. 31227.9 divided by 1 will give you 31227.9 the mean square. 8968.1 divided by 43 will give you 208.6. How do we get the F? The RF is 31227.9 divided by 208.6. Please take notes. There's some mathematics involved. So the F statistic here is 149.73. The p-value associated with that is what you see. It is a p-value that we actually going to compare with the level of significance for us to take a decision of whether we can have a significant difference or not. Now, the summary of what we did today is just like you through how we can decompose, okay, how you can decompose, how the variation around the dependent variable can be decomposed into explained and the unexplained variation. And I walk you through how to do that manually, and of course how you're going to do that in R, which is what my TA will actually walk you through in the lab this week. Before I go, I'm going to make an announcement about those who attend lecture online, because I know midterm exam, just like the way they say election as a consequence, right? Exam also as a consequence. So the only way I believe students can pass is when the students actually attend lecture and they pay attention. They don't understand, they ask question. I'm going to send a message and I'm going to give a condition under which students that we want to attend my lecture online, if you want to attend my lecture online, because I will keep on asking a question whether they can hear me or not. Okay, because I don't want a situation whereby some people they will pretend as if they are attending lecture online. They will just log in and they are somewhere else. I will never tolerate that, because I know you guys pay for college. To pay for college education in the United States is not only in the United States, anywhere in the world. It's not easy to pay for college education, and that is why I need everyone to always pay attention. Okay, so those who can attend my lecture online henceforth are those who are actually going to participate in my class. Okay, uh, when I ask question, about like, is anybody hearing me? I need somebody to talk. When you talk, that give me confidence you are in my class. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.